My name is Maya, and this is Lab 3 for Physics 2212. The purpose of this experiment is to determine the relationship between the distance and magnitude of the magnetic field and to determine the relationship between the magnetic field and the magnetic dipole moment. The main principle we are going to be using here is the Biot-Savart law, and we're going to use a couple different derivations of this law, one of them being the magnetic field of a bar magnet and the other one being the magnetic field of a dipole. So to set up this experiment, we're going to use a magnometer app called Firefox, a bar magnet, and a meter stick. We are able to determine where the magnometer sensor is on the smartphone, and we're able to determine where true magnetic north is and account for Earth's magnetic field. And by putting all these together, we're able to create a representation of the magnetic field created by the bar magnet. So the first part of this experiment included some on-axis calculations, determining the magnetic field on the axis of the bar magnet. And we're going to be using the first derivation of the Biot-Savart law, which is the magnetic field of the bar magnet is equal to Kr raised to the n power. If we take the natural log of this equation, we actually get a linear relationship where we see that K is constant and N is constant. And if we plot the natural log of R and of the magnitude of the magnetic field, we're able to get a linear relationship where we see that the slope is negative 1.99, which is equal to n, and this is a little bit of a derivation from the expected n value of negative 3. We're also able to see that the y-intercept is equal to lnk, which is negative 13.08, and our k value is going to be 2.07 times 10 to the negative 6. We are then able to use these numbers to calculate our mu value, and in order to do this we have to assume that n is going to round to negative 3, so this is going to create a little bit of some discrepancies in our data, but when we round that to negative 3 we find that mu is equal to 10.35 amperes per meter squared. When we did our off-axis calculations, we initialized it when on-axis d perp was equal to 1.5 and our b net was equal to 1 times 10 to the negative 4 Tesla. When we calculated our b net, we found that it was equal to 3.38 times 10 to the negative 5 Tesla at an off-axis location of 0.212 meters. We had to calculate B net from the components due to the correction that needed to be done on BY, and this is due to Earth's magnetic field. Once we make that correction, we can find the magnitude of B net. Now, we can take our pieces that we just calculated and put them into our Glowscript code in order to create a calculation for the off-axis magnetic field. We calculated mu mag, which is in the red box, and we calculated d perp, which is in the other red box. And in our green boxes is our function in order to calculate the magnetic field. So in the first green box, we have just the initialization of the function, and then in the bottom green box we are able to apply that function in order to find the magnetic field at our specific location. If you want to see the full Glowscript code, it is linked in the description box. So this is our Glowscript model. We can see that our magnet is our gray bar, the on-axis magnetic field is the orange arrows, the perpendicular magnetic field is the blue arrows, and the 45-degree field is the pink arrow. This is the output from that program, and the important pieces that we want to look at are the experimental versus Glowscript. So the experimental B net that we calculated at 45 degrees was 3.38 times 10 to the negative 5 Tesla, but Glowscript calculated this as 1.71 times 10 to the negative 4 Tesla, which is about 134% difference. I believe that the main cause of this difference is that we had to round our n value in order to find mu in the first place, which was negative 1.9 to negative 3, which is about a 45% difference. So this shows that our experimental setup was not ideal. There could have been interference from other magnetic things in the room, or the sensor was not properly calibrated. So what if we never oriented our experiment to compensate for magnetic north and we just did the experiment regardless? Well, all of our values would be pretty inaccurate because Earth's magnetic field would be included. It wouldn't be taking in data just from our magnet. It would be taking in data from the Earth's magnetic field as well. And if you put two identical magnets together, then we would have the same directions, but the magnitude of magnetic field would double.